Consider the following problem. We're trying to find the electric field of a straight thin rod with total charge Q, length L, where the charge is uniformly distributed, a distance x along the rod axis. So our starting point for this, at least for this first problem, is we're starting from knowing the electric field of a point charge, namely that E is equal to KQ over R squared, R hat. And we'd like to apply this to a continuous charge distribution. Now, since we know the formula for a point charge, the natural thing to do is to say, well, let's break up this rod into a bunch of point charges, and we can go ahead and do that. To break this down into a bunch of point charges, we're breaking it down into an infinite number of points, which means that each of our small charges will have infinitesimal charge dq. And with that, we can replace our formula for E. Instead of E equals KQ over R squared R hat, we will instead have dE is equal to K dQ over R squared R hat. And so let's further illustrate what this looks like. First of all, I've drawn a representative dq. For that dq, I can draw what R looks like. R is the distance between the point at which we want to know the electric field and our particular choice of dq. Furthermore, I can draw the contribution to the electric field due to this tiny charge. I'm going to say that that is dE, and it points to the right since dq is positive. Okay, so that was step one. We drew a picture. We'll try to keep track of our steps here. Now, step two is not going to be super relevant for this problem, but I'll quickly mention it, which is to assess direction. We'll revisit this in the next video. But by assess direction, I mean to look at the direction of dE due to different charges. In this particular case, that isn't super interesting because if I were to look at a second dq prime, right, its dE would also point in the same direction. So we're going to skip this step and revisit it in the next video where this becomes actually relevant. So I'll just put that in parentheses for today. Now, because all of our dEs are pointing in the same direction, what I'm going to do now is drop my vector notation. I know the overall direction will be to the right. And so we'll sort of keep going. We'll say dE is equal to K dQ over R squared, no vectors, which means we can probably just go ahead and integrate to get our total electric field. So how do we carry through this integration? Well, first we'll note, does anything vary with dq, dq being our variable of integration? Well, k is just a number, so we can go ahead and pull that out of our integral. But we'll notice that r is different for different dqs. If I were to draw a dq at this end, the value of r would just be x. Whereas if I draw dq all the way at that end, the value of r is x plus L. And so clearly, R is a function of Q, but not in a way that we find easy to write. So at the moment, we have K dQ over R squared. So we've done step three, check what varies with R, with dQ. And we have found that there are some things which vary with dq. And so that will lead us naturally into step four. Unfortunately, there's no natural way in which to rewrite R as a function of q. And so instead, we're going to do as follows. We are going to use a density to rewrite dq. And so what do I mean by that? Remember that at the start of the problem, we indicated that our total charge was q and our total length was L. Moreover, I specifically mentioned that the density is uniform. So we're going to start by introducing the concept of a density. In this case, we have lambda, which we call linear charge density. And it is always true, by definition, that lambda gives you the charge per unit length. This is always true. Now, in the particulars of our problem, we know the following two things. We also know the value of lambda, namely that it is our total charge over our total length. So that's going to be our starting point. Then we'll mention the next true fact about lambda, but for now, what I can do is rewrite my integral with the density. So we will now have k. Instead of dq, I can now write lambda dl over r squared. And of course, we can also plug in the value of lambda, namely that it is total charge over total length. And I can also go ahead and pull it out of the integral since both of those are constants. All right, and with that, we've done step 4. But we'll notice that r, dl, represents a small element of our line segment, but still isn't a very useful variable. In this case, though, we'll notice that a small segment of our line segment, dl, is equivalent to dx, right? Because our rod is simply aligned along the x-axis. And in doing so, we've started on step 5, which is to introduce a coordinate system. So step 5, coordinate system. And at this point, I do want to mention that dl will not always be dx. I'll post a couple more videos on examples where that's not the case, but just to sort of make that clear immediately, if my rod were a curved rod, dl would not be equal to dx. Hopefully that clarifies that. At this point, we can finish up step 5, go back to our diagram. To be able to rewrite r as a function of x, we should probably be mentioning where x equals 0. So I'll say, let's have x equals 0 be here. And there is a little bit of variable collision going on here. So I'm actually going to quickly rewrite x over here as a to remove any ambiguity. And so if I make x equals 0 be at the point at which I want my electric field to be, I'll choose to make the positive direction of the x-axis point to the left, just to keep things simple there. And so what we can now see is 2 things. First of all, the distance from our point P, at which we want to know the electric field, to dq is simply equal to our x-coordinate, right? We're just marching along the x-axis, right? When I am at a position x equals a, I am a distance a away from point P. And so with this coordinate system in place, I can rewrite r as just x. So we have dx over x squared. And now let's think about our bounds of integration. We're integrating along the rod, which means we are starting at x equals a and going up all the way to x equals L plus a. And there we have it. We can go ahead and integrate. The integral dx over x squared, well, that's just going to be negative 1 over x evaluated from a to L plus a, which leaves us with kq over L times negative 1 over L plus a plus 1 over a, which we can, of course, simplify somewhat, but I'll just leave it at this. One last note before we wrap up this video. I encourage you to redo this problem using a different coordinate system, a couple of choices. But another natural choice of coordinate system would be to choose this point on the rod to be your 0 point. This would change how r varies with x. And so definitely give that a try. See that you get to the same solution.